Hello and welcome. This is Physics 1401. Today I'm going to try to solve some physics problems from the chapter about force. And I'm just going to pick some problems from this chapter, chapter 2. Let's start with the section about graphical vector addition. Alright, so there are a couple of problems with pictures, and there's a problem here without any picture. Let's see what it's saying. Huan is helping his mother rearrange the living room furniture. Huan pushes on the armchair with a force of 30 newtons. Let's just write it down here. So problem number 10. This is a force of 30 newtons directed at an angle of 25 degrees above a horizontal line. Okay, 25 degrees above the horizontal, while his mother pushes with a force of 60 newtons. So let's call this one F1 and his mother will be F2. 60 newtons directed at an angle of 35 degrees below the same horizontal. Okay, above and below the horizontal. What is the vector sum of these two forces? What is the vector sum of these two forces, F1 plus F2? Use graph paper, ruler, protractor to find a graphical solution. Okay, so we'll need a graph paper. Let's change the background. Alright, format background. Let's see what options we have. We have graph paper. Okay, is this good enough? Maybe denser. I think that's all. Well, narrow. Okay, narrow lines. There's square. Okay, square should work, I guess. Square can work. Graph paper. Well, these look larger. Let's just stick with this one. Okay. And protractor, well, we have this ruler here. I'm going to use the ruler. Alright, so now first the notation, okay? As long as you keep the arrows on top of the vectors, here F1 and F2, you are allowed to write the sum like this, okay? Please do not write it as F sum equals F1 plus F2. Because if you drop the arrow, it means the magnitude. Alright? You know, the magnitude can be written like this, which is equivalent to putting bars next to the vector. Alright? So keep in mind, this equation on the left is correct only when you keep the arrows on the top. So do not use this. This would mean the magnitudes are added, which we're not doing. Okay, so this is about the graphical addition of these vectors. We use the graph paper, ruler, and protractor. Okay, so let's start with the horizontal. They mention a horizontal line. So let's start with drawing a horizontal line. Okay, here's 0 degrees. Alright. So if let's use white, red, okay, red is fine. This is the horizontal line, alright. And actually, maybe it's better if I just align it with the squares, huh? So let me move it up a little bit. start over. So let me line up with, yeah, that's better, I guess. Oops. Okay. So here's right. This is horizontal. Anyway, so F1 has to be 25 degrees above. So I have to rotate this. It doesn't say right or left, so I'm just going to pick right. Right direction, 25 degrees. All right. So I'm going to place this somewhere along this line. Let's say right over here. Okay. So along this direction will be my F1 vector. Now I have to decide how long should it be. It says 30 newtons. Okay, 30 newtons versus F2, which is 60 newtons. Okay, so if I, like this ruler is in inches, I believe. If I pick 2 inches, let's go, 2 inches, that should correspond to 30 newtons. If I double it, it'll be 60, I know, okay? If you're wondering, why didn't I use 3 inches? I could, doesn't matter, I mean, whatever is easy for you, if you're just scaling in that way. So let me take this out of the way. So this is my F1. I'm just gonna make it like an arrow, okay? So this is my F1 with 25 degrees above the horizontal. Now the second vector is F2, and F2 should be 35 degrees below the horizontal. So I have to rotate it the other way around. Oops. Oh, okay. Well, I didn't want to zoom in, I just wanted to rotate it. Okay, let's rotate it to 35. 32, 34, 35. All right. So I'm just going to carry it to the tip of the first vector there. All right. And the scaling should be now for 60 newtons, I have to have 4 inches. 1, 2, 3, 4. Okay, so this is my F2. F2. Now why did I put F2 over there? Because I'm following the tail to tip rule. Okay, I know that if I start from the tail of F1 now and connect it to the tip of F2, that'll give me the sum of these two, right? So I'm going to take my ruler. Now I need to rotate it a little bit to the left, this way, and carry it around until I can get a line through each point, approximately something like this, right? Like that. Okay, that's good enough. Okay, let's show it with green. So this will be the sum. Oops, I didn't want to do that. Okay. Alright, so let's get rid of the ruler. This is my sum. Alright, that's the graphical addition. Now, there's an alternative way to do it. You could actually start F2 from where F1 starts. Okay, you could extend it just like that. So in a parallel fashion. But then you would have to construct the parallelogram, and then create the diagonal line, which would be exactly what I drew here, F sum. Okay. But now we're not done. we're not done because we only have the picture of it. We have to find two things. Number one, what is the magnitude of the result? In other words, what is this? And the direction. Direction meaning maybe this angle here. Call it theta. Okay? So what is theta? Okay, so what I need to do is, actually I need to use the protractor if you have one, or I can use this ruler again here. Okay, actually you know what? I already know the direction. It's 14 degrees, right? It's 14 degrees below the horizontal. 14 degrees below the horizontal. I just need to measure the length. Okay, so let's start from here and just count it. 1, 2, 3, 4, 5, 5.5. Okay, so the length is 5.5, 5.5 inches. Right, let's do it again. 1, 2, 3, 4, 5. Very close to 5.5 inches. Alright, let's get rid of the ruler. But now we have to convert 5.5 inches to newtons. If 30 newtons is represented by 2 inches, it's pretty much 15 newtons per inch, right? So if you multiply this by 5.5 inches, you get the answer in what? In newtons. Alright, let's do it. 15 times 5.5, that is 82.5. 82.5 newtons. Alright, that is the sum. What is the vector sum of these two forces? We found the sum. Let's check this result. How? Well, we can use the component method. That's not part of this problem, but we can always check our result, right? So, check this using component method. Which will be the next topic in this list anyways. So let's do it. Check this using component method. What is the component method? Let's remember, if I can write the sum like this using the vector notation, it is a vector equation. And remember, every vector equation contains two equations. Okay, we're in 2 dimensions, so it contains 2 equations in it. One for the horizontal, or sometimes you can call it the x, if you call this axis x, and the other one is for the vertical. These are the components, right? Call it y. So in other words, you get 2 equations out of 1 equation. The x component of the sum will be equal to the x component of f1 plus x component of f2. See, I dropped the arrows now because I'm only working with components. Similarly, the y components of f1 and f2 will add up to give me the y component of the sum. Right? So now it's about finding the components of these vectors. Remember, we have x and y as the Cartesian coordinates. So the vectors that we're talking about here, f1, let's use the other way. Let's put f2 here now, just to make a point, right? So if I'm talking about f1x, for instance, I'm talking about the projection of this vector along the x direction. So this is what I'm after. Alright? So this number, this is the actually length of the side of that right triangle. f1x is this coordinate here. f1x. f1x. Similarly, if I do it for f2y, I'm talking about the projection along the y-axis, so this will be f2y. Okay? f2y will be actually negative, as you can see, it's below the origin. So how do we find these four components? We use basic trigonometry. Okay? So this is, what was the degrees? 25, and the other one was 35. So we have here 25, and this one is 35 degrees. The length of f1, which is 30, and remember I didn't draw this to scale, actually f2 is twice longer, right? But I just did a quick sketch here, so don't worry about the picture here. But those are the hypotenuse. Right? The hypotenuse corresponds to the length of the vector. And now all we need is the basic definitions of cosine and sine. Alright? Cosine and sine. Now take this triangle, for instance. Just for this case, I'm going to do it separately. Just in case you don't really, if you don't see it over there. Let me just do it from scratch here. I'm saying this side has a length that corresponds to 30 newtons, all right? But we want to find this. And we know that the angle here is 25 degrees. So basically I want to find the side of the triangle, side adjacent to 25. So this reminds me the cosine function. Because cosine of any angle is side adjacent divided by hypotenuse. So if you multiply both sides by hypotenuse, you get the adjacent side, right? So f1x, this positive number, this point here, which is also the length of that adjacent side, is nothing but 30 times cosine 25. 30 newtons times cosine 25. Okay, so you just find this number. And then, using your calculator, let's do f2x using same logic, okay? Now we have the 35 degree over here, and we're talking about this right triangle over here. But this side that we're trying to find, which is f2x, is also the side adjacent to 35. So I should write here 60 newtons, because that's the length of f2. 60 newtons times cosine 35 degrees. Alright. What about the y components? F1 y right there. this is what we want to find. F1, y, which corresponds to side opposite. If we're now talking about the opposite side, it has to be associated with the sine of that angle. All right? So basically, opposite divided by hypotenuse gives me sine. Therefore, the opposite side is equal to hypotenuse times the sine of the angle. So 30 newtons times sine 25 degrees. What about F2y? F2y has to do with this side of the lower triangle, which is equal to that side. I can use sine 35, but keep in mind F2y is a negative number. It's below the origin, right? So I just put it there by hand, negative 60 newtons times sine 35. All right? Now, this is the easiest way. It's not the only way. Maybe I should show the alternative methods, which will give you the same answer in a different problem. Let's just take these four numbers and plug them into the equations above. All right? So I'm just going to do that. The first equation, let me move it up a little bit over here. So from the first equation here, I get f sum x, meaning the x component. I just need to add this one to which f2x, this one. So 30 cosine, let's make sure it's in the degrees but not radians. Can't see. Okay, let me change it to radians. It's degrees, I'm sorry. Set up angle unit degrees 1. All right. So 30 cosine 25 plus 60 cosine 35 equals 76 point, it goes like 338. Let's just take one more digit after the decimal point. 76.3 newtons. And similarly, f sum y will be this plus that. Okay, so 30 sine 25 minus 60 sine 35. And that gives me negative 21.7 newtons. All right. So what I just found is hopefully the x and y components of this sum, f sum. Okay. Now how do I go from here to the actual length of f sum, which I want to find? Okay, how do I find that? Well, so this is what I have now. This is the x, this is y, or let's put y over here. This is the vector. I want to find the length of this vector. All I know is these numbers. Okay, this is the origin here, but that number is what? 76.3. And this one here, negative 21.7, which corresponds to this side. That's 21.7, which also corresponds to this side, 21.7. And this side of the right triangle here is 76.3. So how do I find hypotenuse? Very simple, right? Use the Pythagorean theorem. So f sum is the hypotenuse that squared is equal to square of the other two. Square of one plus the square of the other, right? So if I take the square root of that, that gives me the hypotenuse. So 76.3 squared plus, what is that, 21.7 squared. You're going to use this formula over and over in this class, okay? So 76.3 squared, where is that squared, plus 21.7 squared. Take the square root of this, 79.3. 79.3 newtons. Now, is this close to what we found earlier? I mean, not too bad. 82.5, 79. Well, I would say 79.3 is actually the exact one. The one we measured here is not exact because there's always some error, right, when you're lining up the vectors and measuring using protractors and rulers. You can have some error there, which is not a big deal, but we're in the ballpark of 80, okay? So 79, 80, these are all okay. What about the direction? Now, this one, we found it to be 14. 14. How close were we to the actual direction? So let's say, what about the direction? Meaning this angle, right? This is supposed to be 14 degrees. Is it? Okay, so which trigonometric function do you want to use? You can use sine, cosine. We haven't used tangent yet, right? Let's use tangent. So use tangent. So tangent of an angle is equal to the opposite divided by adjacent, right? So tangent theta is equal to opposite, which is 21.7 divided by 76.3. Okay, as you see, I'm just using the actual length of the triangle. I'm not using the coordinate. I could use the coordinate, you know, and that would give me a negative, actually, theta, which would tell me that it's below the x-axis. But it's okay, I mean, I can just go with my triangle here. As long as I know what I'm doing, there shouldn't be any problem. So I'm just using the sides, 21.7 over 76.3. That's a tangent, but I want theta, so what do? I use the arctangent. Arctangent. You can also write it as tangent to the power negative 1, right? Just notation, or just write arctangent, the same thing, doesn't matter what you use. Arctangent, same thing. So 21.7 divided by 76.3. If I take the arctangent, is it going to be anything close to 14? If yes, we're good. So 21.7 divided by 76.3. 0.28, take the arctangent, shift 10, answer 15.87, about 15.9. 15.9 degrees, okay? Well, this one is exact, all right? So that's why the component method is much better, right? I mean, you don't find the protractor and ruler, you know, at hand all the time, you know, and then when you use them, you can make mistakes unless you're really careful, like an architect, you know, very careful. But we were close, okay? 14 degrees, 16, just 2 degrees difference is not a big deal. But these are the exact values. The component method works better. Okay, so I'm not sure if I should spend more time on the graphical method. I think you get the idea. So let's solve one more problem from vector addition. I don't know which one. Let's do the last one here, 26. Okay, I'm going to clear canvas. Let's go back to 100% zoom. Okay, so this is number 26. It says vector B has a magnitude 7.1. So vector B has a magnitude equal to 7.1 units, whatever unit is, and a direction 14 degrees below the x-axis. Let's call it theta. 14 degrees below. Now I'm going to change notation. I'm going to use a negative sign. Remember I said you can, there's an alternative way. So theta is negative 14 degrees. The negative sign just means below the x-axis. Below the x-axis. Okay, that's B1. Pretty much we know everything about the vector with these two. What about C? Vector C has x component. Okay, now we're talking about C, another vector, but we're given the components. Cx is negative 1.8, and the y component, Cy, is negative 6.7. Are we recording, by the way? Let me check quickly. Yes, it's still recording. Good. So this is the y component. So pretty much we know everything about the vector as well, the C vector as well. All right. Compute the x and y components of B. So for part A, find the x and y components of B. And for part B, the magnitude and direction of C. What is the magnitude of C? Right. Now check it out. Both x and y components of C are negative. What does it tell me? Both components are negative numbers. Now the positive x are here, the positive y over there, but these numbers are negative, which tells me that the vector I'm looking for, meaning C, is actually in the third quadrant. That is my vector C. Okay, remember the quadrants. This is the first quadrant, second quadrant, third quadrant, and the fourth quadrant. I need to find the magnitude of C. I also need to find the direction of C. So for direction, let me use a symbol. I already used theta. Let me use phi. Now I'm going to measure phi. I can measure phi from any axis that I like. Who cares? I mean, it's not in the book, so I can come up with anything. But just to make it different, I'm going to measure it from the x-axis. Like this. So this will be my phi. Obviously, phi is greater than 180 degrees. You can see that, right? So that's the second part. What is the C? What is the magnitude of C? And also find phi. And there's the third part. The magnitude and direction of C plus B. Magnitude and direction of the third vector, which is found by adding B to C. Okay, what is the magnitude and what is the direction of this vector? We're going to use component method, okay? We're not using protractor or graph paper or anything like that. We're just going to use the components. Now, let's start with part A. Now, which quadrant are we talking about for B, vector B? The magnitude doesn't tell you which quadrant it is in. but the angle gives you a clue, right? The book says below the x-axis, and I wrote it as negative, so we know that we're talking about a vector that looks like this. Okay, so it has to have a positive x component and a negative y component, right? So the bx and by we're looking for will be here. This is bx, and this one will be by. Okay, so let's use our sines and cosines then. Oops. Okay, so we're talking about the length here, which is the hypotenuse, that's 7.1, and this is 14 degrees. Now how do I find this side, which is the opposite side to 14, and how do I find the adjacent side to 14? Just use the definitions of cosine and sine, but you have to do it the right way, okay? Don't never confuse sines and cosines. That would be a big mistake, and there is no room for any mistake when it comes to sines and cosines. Okay, cosine is adjacent over hypotenuse, and the sine is opposite over hypotenuse. Alright, so the opposite side over hypotenuse, this gives me the sine of 14 degrees, and side adjacent divided by hypotenuse gives me the cosine of 14 degrees. So how do I find these sides? Just multiply 7.1 by sine 14 like we did before, and the adjacent will be found by multiplying 7.1 by cosine 14. Okay, so let's just do that. What is it? 7.1 sine 14, 1.72. Okay, or you can just say 1.72 when I keep two significant figures. What I do is this. I mean, yeah, the magnitude is given in two significant figures, but I'm not done with my calculations yet. Okay, so it's okay to keep three significant figures, and when you're done, you can reduce it to two. No problem. Okay, that's better actually. So let's find the adjacent side. That's 7.1 times cosine 14. And that gives me 6.89. All right. You want to check that? Take those adjacent and opposite, take the squares and add them. See if you can get 7.1 again, all right? Just to check it. So 6.89 squared plus 1.72 squared. 6.89 squared plus 1.72 squared gives me 50.43. Take the square of 50.43. Take the square root of this. 7.101. I mean, you don't have to fill all the digits. All you need is actually two significant figures, okay? So you just take these two. And that indeed matches the thing we started with. So it checks. Anyway, so have we found bx and by yet? Not exactly, because by has to be negative, right? So when I write these, I gotta be careful. Bx is 6.89, but by, I need to put a negative by hand in front of this number here. Where is it? 1.72. 1.72, because we're talking about a negative number over here. Okay? So you either do it like this, meaning you just draw, if you're a visual thinker, draw your right triangle and see which one is adjacent, which one is opposite, and use your trigonometric skills and find those sides, and then decide which one will be positive, which one will be negative, depending on the quadrant the vector points at. Or, if you don't want to do all of that, there's even a simpler way. Or, stick with the rule, the x component uses cosine and the y component uses sine. But this comes with a risk, okay? You can easily make a mistake. You have to make sure that the angle is measured from the x-axis, okay? That's the thing. When the angle is measured from the x-axis. If the problem given has an angle, but that is, let's say, this one here, measured from the negative y-axis, I would suggest use your triangle method, okay? Locate your right triangle and see which side is which and use your trigonometry. Now, if you know the angle from the x-axis, now in this case my B is this way, right? By an angle measured from the x-axis, I mean this. Alright? Now, if you know what that is, you can just use it. Take the cosine of that, multiply by B, and you get the x component. Take the sine of that angle, multiply by the magnitude of B, you'll find the y component. Okay? Now, you can use that green large angle, or you can use this version, which is the one we're given, but keep that negative there, okay? So this is actually negative, what was that? Negative 14 degrees. Or use the other one. I'm going to show you that both actually work, right? So this angle here is nothing but 360 degrees minus 14, which is 346 degrees, right? So Bx is B times cosine of this angle, call it alpha, and By is B times sine of alpha. So let's plug in those numbers and see if we get the numbers we found earlier. B was 7.1 times cosine 346. Okay, 7.1 cosine 346, and that is 6.89. So it checks. 6.89 checks the other one. What about By? That is 7.1 times sine 346. 7.1 times sine 346. That is negative 1.72. That also checks. See, the negative sign here showed up automatically on your calculator. You didn't have to put it by hand, which we did earlier when we considered the triangle and then used the definition of sine and cosine based on our right triangle here, and then said, okay, since the vector is pointing in the fourth quadrant, its y component has to be negative, and then we put that negative here by hand. Okay, that's okay, no problem with that. But alternatively, you could use a simple formula. The x component goes with the cosine and the sine goes with the y component. You just plug them in, the negative sign automatically goes there, as long as you use the angle which is measured from the positive y-axis. Now I used 346. What would happen if I had used, what if I use a negative 14? Let's do it. Alright, see, I'm giving you alternatives. Just pick the one you like the best. Or bx is equal to 7.1 cosine of negative 14 degrees, and by is equal to 7.1 times sine of negative 14 degrees, and check it with your calculator, okay? 7.1 cosine negative 14, 6.89 as you expected, and 7.1 times sine negative 14, that is negative 1.72. Alright, so if you use this method, whether you use the angle, the positive angle or the negative angle, they point to the same direction. You don't have to worry about triangles, and you don't have to remember the definition of cosine and sine, which is not a big deal, I'm just telling you. Just use the fact that x component is cosine, y is the sine, always, as long as you measure your angle correctly. Okay? This is the alternative method. If you don't want to draw your, maybe you're a visual thinker and you locate your triangles immediately and you don't have to go through this. Okay? I'm just leaving that to you. I'm giving you options. Alright, let's come to part B now. Part B is about the other vector, which is C. C was in the third quadrant. Remember, C was in the third quadrant, and this means both x and y components are negative. What we want to find is the magnitude of it, meaning the length of the vector, which is the hypotenuse. Alright, you just take the squares of these and then take the square root. That's going to give you the hypotenuse. We did it before. Let's do it again. The magnitude of C is equal to the square root of cx squared plus cy squared. Now you can think of cx and cy as the given coordinates, or you can think of them as the sides. This squared plus that squared equal to the hypotenuse squared, okay? Either way, okay, let's use the coordinates. Cx was negative 1.8. Take the square, and the y component was negative 6.7 squared. Okay, if you don't want to use the coordinates, if you just want to think in terms of the sides, of course they won't be negative, but you're squaring them, doesn't matter, right? So 1.8 squared, oops, not 1.5, 1.8 squared plus 6.7 squared, and take the square root, of course. That is 6.94. Or 6.9. That's the length of C. What about the angle? Alpha. We define alpha to be this angle, not alpha, phi. We define phi to be this. And the reason is, I'm just going to use the arctangent here. Arctangent cy over cx. This will be equal to phi. Okay, so you can take this as a formula. Just like we had this relationship between the x component and the cosine and the y component and sine, we have this relationship with the angle here. Take the arctangent of cy over cx. This will give you the angle measured from the x component. Alright, so you gotta be careful with the signs here. If cy is negative, use negative, right? So cy is negative 6.7 and divided by x. X is also negative, negative 1.8. Now, there's a very interesting thing going to happen here. You'll see in a minute. But let's find this. So 6.7 divided by 1.8. That is 3.72, and then take the arctangent. Now this is 74.96. 74.96 degrees, but there's a problem here. Okay, there's a problem. Well, what we're looking for was an angle which was greater than 180, but this is what we get from our calculator, 74.96. How could it be? Okay, how can it be? Well, the calculator doesn't know everything. It doesn't know that our vector lives in the third quadrant, for instance, right? Because remember, we're dividing two negative numbers. It's the same as dividing 6.7 by 1.8. So it could be as well in the first quadrant. Now, how would the calculator know about it? It doesn't know. You know it. So you gotta add that 180 by hand, okay? So add 180 degrees by hand. So the real phi that we want to find is 180 degrees plus 74.96. Okay, so just add 180 to this number. 254.96. It's close to 255. 255 degrees. All right, check it. Check your answer. How are we gonna check? Easy. Check it with CX, for instance. CX. What is CX? CX is the length of C, which was 6.9, times cosine of this angle, 255. Or 254.96 if you want to be exact. Okay? So 6.9 cosine 255. That gives you negative 1.78579, which is negative 1.8. Indeed, that's the case. All right, so it checks. So that's how you find the direction of C. If you want to if you don't want to use arctangent, if you just want to use the good old triangle method, you can. Then you have to say, hey, I'm looking for this angle now over here. Okay, and this angle here, I'm going to give it a name. I'm going to call it gamma. Gamma. Now I want to use cosine. So cosine gamma is equal to this side, which is adjacent, divided by hypotenuse. Hypotenuse, which means gamma should be the arc cosine of adjacent divided by hypotenuse. And what are those? Adjacent means the length of this side of the triangle. That's nothing but the this one, 1.8. 1.8. Okay, and hypotenuse was the length of C, which was 6.9. 9. Okay, so you divide 1.8 divided by 6.9, 0.26, and take the arc cosine of that, you get 74.8. Which can be approximated as 75, let's say, okay, which matches this actually, right? Or 74.9, if you will, doesn't matter. So, you can use arc cosine if you don't want to use arc tangent. Okay, so as long as you know what you're doing, you have many ways, you have alternatives. Okay, of course, you're not going to spend this much time on just one problem, but I wanted to show you all the options. Okay, so hopefully, oh, there's one more, we're not done yet. So part C, find the magnitude and direction of B plus C. Okay, let's do that. So part C is about adding B to C. Let's call this vector A. Okay, so what is the magnitude of A? And what is the direction of A? Okay, we're using the component method. Means AX is equal to BX plus CX, and AY is equal to BY plus CY. Let's just copy these numbers from the previous. So BX was 6.89 and CX was negative 1.8, and the BY was negative 1.72, and CY is negative 6.87. I'm sorry, negative 6.7. Okay, so 6.89 minus 1.8, that is 5.09, 5.1, let's say, and negative 1.72 minus 6.7, that is negative 8.4. Those are the x and y components of A, from which we can find the magnitude of A. Square root formula, right? 5.1 squared plus negative 8.4 squared. 5.1 squared plus 8.4 squared. 96.57, take the square root of that, 9.8. Okay, that is the magnitude of the sum. What about the direction? Now, which quadrant are we talking about? AX is 5.1, somewhere here, and AY is negative 8.4, over here. So we're talking about actually the fourth quadrant. Alright, so we're talking about the fourth quadrant. And let's use arctangent again. Arctangent of AY over AX. Okay, so AY is negative 8.4 and AX is 5.1. So negative 8.4 divided by 5.1, negative 1.65. Take the arctangent of that. This is negative 58. Right, negative 58.7 degrees. Okay, negative means it's below the x direction. All right, so any angle below the x-axis will be negative. Okay, so this was question number 26. Now let's come to the next section, inertia and equilibrium. All right, so let's solve an equilibrium problem. Okay, let's find the picture. Let's find a problem with picture. Okay, so I have a couple here. Now, well, 34. 34 is kind of easy. 34 is easy. Let's do 35. Let's do 35. Okay. What does it say? Two forces of magnitudes 3 newtons and 4 newtons act on an object. Two forces, F1. Magnitude 3 newtons, and the second force has a magnitude of 4 newtons. Act on an object. How are the directions of the two forces related if A, the net force has a magnitude 70 newtons. The net force. Net means vector sum. F net means the vector sum of F1 and F2. But the magnitude of the net force is what? 7 newtons. Okay, so what is the relationship between the directions of F1 and F2 if the net force is just 7 newtons magnitude? And then you repeat this for 5. Part B, the net force is 5 newtons. And part C says what relationship between the directions gives the smallest magnitude net force, and what is this magnitude? Okay, let's worry about C later. Let's just find A first, and B will follow from there. Okay. Now obviously F1 and F2 are simply added in part A. Okay, I mean you don't even have to do anything, right? I mean 3 plus 4 is 7. There's not really much to do there. For part A, they must be in the same direction. 3 newtons in this direction, and then 4 newtons in the same direction. If you add these, right? If you bring that 3 newton over here, 3 plus 4, you will get 7 newtons. So the relationship between the two is 0 degrees or parallel. Parallel vectors. Okay? So A was easy. What about B? B says 5 newtons. Okay, what will be the next easy case? What if they're opposite, in opposite directions? Well, if that were the case, you would subtract 3 from 4, you get only 1. The net force would be 1, okay? Maybe that's what they're asking in part C, but that's definitely not part B, okay? We gotta find 5 newtons. All right, 5. But this one also doesn't require too much thinking, because if you remember from trigonometry, there are special triangles. Special means some right triangles with sides as whole numbers, okay? And this is one of them, 3, 4, 5 actually. So I picked an easy problem, huh? So the 3, 4, 5 triangle. 3, 4. This is 5, meaning 3 squared plus 4 squared, that is 9 plus 16, which is 25. Take the square root of 25, you get 5, okay? So, if these two vectors, f1 and f2, are perpendicular, if they are perpendicular, 3 newtons, and then you have 4 newtons. Their sum, let's use the parallelogram, which becomes just a rectangle, and then the diagonal shows me the sum, right? This is 5 newtons, of course. And we're done, all right? So the relationship between the angles is that they are perpendicular. You guys know the symbols of perpendicular and parallel? Parallel is this. 2 lines like this. This means they're parallel. If they're perpendicular, you use an inverse T like that. F1 and F2 are perpendicular to each other. Okay. Okay, so let's read part C again. What relationship between the directions gives the smallest magnitude, net force, and what is this magnitude? So, minimum F net. How can we obtain minimum F net? I think I just told you. What if they are in the opposite directions? So we have, let's say, 4 newtons pointing to the right, and we have 3 newtons pointing to the left. The net force will be, okay, you can carry 3 here if you want to do it formally. You carry it over here, and then the tail to tip rule tells you that this is actually F net. Okay, so the magnitude of F net will be 4 minus 3, 1 newtons. Okay, so that's so what is the angle then between the two vectors? 180 degrees. These two are 180 degrees apart. Okay, if I use the notation with unit vectors, for instance, use unit vectors. Suppose this is the x-axis. Then F1, that is the, which one was F1? F1 was 3. So 3 is pointing to the left, right? So F1 is actually negative 3 newtons times I hat. Or I think the book uses x hat. Remind me which one does the book use? Let's stick with the notation the book uses for unit vectors. I think in the video, last time I mentioned both of them, I hat or x hat. Both are used. These are the unit vectors, right? Okay, I can't see in the book. I don't know where it is. Oh, they use x hat. Okay, so let's just use x hat, or negative 3 newtons x hat. So F2 is Well, it's pointing to the right, so it's positive 4 newtons. Exit. Okay. All right. So that's part C. This was the equilibrium problem. What else? Interaction pairs. Newton's third law of motion. Okay, we talked about it in the last video. Newton's third law. So let's find a problem. I don't know which one. Let's do last one. 47. A woman who weighs 600 newtons. Weight is 600 newtons. Let's call it W, okay? W stands for weight. Sits on a chair with her feet on the floor and her arms resting on the chair's armrests. Okay, do I need to draw a picture for this? Okay, well, let's give it a try. So here's the chair with some arms. And this is the legs, okay? So that's the chair, okay? This is not too bad. The chair is on the floor. And we have a woman. Okay, I'm just gonna draw a stick figure here. Okay, so with legs and arms, of course. Okay, not very good, but it's okay. Let's make the arms bigger. Alright, so the chair weighs 100 newtons. So this is the weight of the woman, but we also have weight of the chair, which is 100 newtons. Each armrest exerts an upward force of 25 newtons on her arms. Let's change color. Let's use green. The armrest exerts a 25 Newton force on the left arm, and also on the right arm. It exerts an upward force of 25 newtons. Good. A. What force does the floor exert on her feet? Okay, interesting. So, what force? Well, both feet, right? So, we have to place two forces here. Okay, let's call F and F. Okay, so these are the both feet. Okay, both feet are there. That's part A. What is F? Part B. What force does the floor exert on the chair? Okay, well, the chair has 4 legs. Now, are these forces equal? That's a legitimate question, right? Is the weight distributed properly? There's nothing in the problem that mentions that, so I'm going to assume these are all equal. Alright. And part C. Consider the woman and the chair to be a single system, okay? Draw a free body diagram for this system that includes only the external forces acting on it. So for part C, the chair and the woman will be a system, in which case we don't have to, for instance, worry about the 25 Newton force, right? Because that's an internal force. We only have to show the external forces. And that system will have these forces from the floor as external, besides, of course, the combined weight, all right? So let's start with part C then. Part C, draw a free body diagram. I'm just going to put a circle here representing the combined mass of the chair and the woman, okay? So this is chair plus woman. Now, what are the forces, external forces acting on this system? Well, we have the weight of the woman and we have the weight of the chair. A combined gravitational downward force, which will be equal to 600 plus 100. You can show them as separate forces if you like, or just one single, but then write at 600 plus 100. So that's equal to 700 newtons downward. All right, and then we have the normal force that the floor exerts on our system, which is upward. And what do we have there? We have actually these two F's, and we have 4 of these F primes. Okay, so we have these. There's one more information I didn't write here. That was the seat of the chair. The seat of the chair exerts an upward force of 500 newtons. The seat exerts on the torso, or on her, let's say, and that's an internal force, so we don't have to worry about it for part C. But let's just show it on the picture here. So right here, there's a force of 500 newtons. Okay, but that 500 Newton doesn't show up in the free body diagram for the chair plus woman system because it's an internal force. We only worried about the external force, okay? So the external forces are, again, the gravitational pull of the Earth, which is in total 700 newtons. That's simply the weight of the chair plus the weight of the woman. And then the force that the floor exerts on the system, which is this green arrow here. And inside that we have all these forces that the surface exerts on her legs, on her feet, and on the legs of the chair. Okay? Okay, so if you want to find this force, it's actually really simple. Okay, the system is in equilibrium. So this force, the 2F plus 4F prime, has to add up to 700 newtons. Okay, if it were anything other than 700 newton, the system would be actually not in equilibrium, right? So we already found part C, that's 700 newtons. What about part A? Part A was, what force does the floor exert on her feet? So what is F here? Part A, what is F? And part B, what force does the floor exert on the chair? F prime. Now to find this, we have to consider our system as, let's say, the woman first. Okay, let's start with that. Now, if I draw a free body diagram only for the woman, what happens? In other words, I'm isolating her. This is my system, okay? The system is only the woman in this case. I'm isolating the woman. What are the external forces that are exerted on the woman? Well, we have her weight, which is downward. And this was 600 newtons. And what else do we have? We have the seat. The seat is pushing her up with a force equal to 500 newtons. And the arm rests exert an upward force of 25. Now I took this to be separate, so if we stick with that, we have 25 here, 25 there. They add up to give me what? 50. 50 newtons from the armrest, right? This is 25 plus 25. Okay, so we already have a total of 550, but that's not enough to compensate for 600 newtons. We need 50 more. And that's going to come from the force the floor exerts on her feet. This was 2F. One from right, one from left. So 2F, but that's equal to 60 minus 500 minus 50. 600 minus 500 minus 50, which is 50. Which makes F equal to 25 newtons. All right. Now, keep in mind, this is based on my picture. What I understood from the wording of the problem is each armrest exerts an upward force of 25. Okay, so I understood correctly, right? And then I thought that the feet will experience equal forces, so that's why I divided by 2, and then you get 25. All right, that's part A, right? F is 25. Now, what about the chair? Okay, if we take the chair as a system, what happens? This was part A. Now let's focus on the chair only. So I'm going to draw a free body diagram. I'm just going to put something here that represents my system, but the system is the chair. Okay, again, I only need to show the external forces on the chair. What are they? I have the weight of the chair. This was, 100 newtons. It's always downward, okay, 100 newtons. And then I have the floor pushing it up, okay, a normal force in a way. So what are those? Those are what I called F primes. And I have 4 of them. So I'm just going to write here 4 F primes. It's pushing it up. Am I done? No, I'm not done. Why not? Because the woman also exerts a force. Okay, this is the action. This is where the action-reaction principle comes in. Okay. Now, if I'm drawing the free body diagram for the chair, I do not have to worry about the interaction between her feet and the floor, which is F, right? Those two green forces. I don't care about those. Those are not part of my problem. My problem is just what happens to the chair. Okay? So she basically exerts a force on the chair. how many interaction points do I have, interaction surfaces? I have the seat of the chair, which carries her weight, most of the weight, and this was 500 newtons. And I also have the two armrests, okay? Now, if the chair exerts a 500 Newton upward force on the person exerts the same force onto the chair, okay? So I have to add that 500 Newtons, which will be downward. 500 Newtons. This comes from the woman. Woman exerts a 500 Newton force, which is downward. Okay? Is that all? No, because I also have these two 25 Newton forces. Just like the armrests push the arms upward, the arms push the armrests downward. Action, reaction. So 25 plus 25, I have 50, which is also downward. And this 50 comes from the arms. Okay, so that's all right? That's all. These forces should add up to 0. That's how we have equilibrium. So this gives me exactly what I need. So 4F prime is equal to 50 newtons plus 100 newtons plus 500 newtons. That's actually 650. That's 4F. So F prime means 650 divided by 4, 162.5 newtons. Okay, so each leg will experience this many newtons. This was 47. You know what? Let's check the answer. Let's make sure we got the numbers correct. Chapter 2, 47. Okay, so chapter 2, 47. Okay. Part A says 50 newtons upward, total for both feet. This was part A. 50 newton for both feet. Each feet is 25. That's what I assumed. Fine. Part B, 650 newtons upward. That's what we found. 650 newtons upward. Again, I assume that each leg would carry the same. Doesn't have to be the case, okay? I mean, you can lean on the front or back. You may distribute your weight not evenly on the legs, so that was an assumption on my part. You have to add an assumption. The total is 650, fine. And part C, we did part C, okay? We did the free body diagram. Actually, they don't really ask a numerical answer for part C. It was just the drawing of the free body diagram. And yeah, we have it. Okay, so this was about equilibrium and Newton's third law. Alright, so okay, what about the next section, gravitational forces? Okay, gravitational forces. Let's pick any problem. Do we have any pictures? The first thing I look at is, does the problem have nice pictures? I don't see any pictures, so I'm just going to read it then. Okay, let's pick, I don't know, Okay. Let's do 59. Okay, it says something about a satellite. We'll find out. 59. Let's solve two problems from this section, okay? 59. Find the ratio of Earth's gravitational force on a satellite when it is on the ground to the gravitational force exerted when the satellite is orbiting at an altitude of 320 kilometers. Okay, interesting. So, here's the Earth, and the satellite is just sitting on the ground first. Okay, here's our satellite waiting to be launched in a lab, and there's a gravitational force on it. Let's show it as, what do you want to call it? F1. Alright? And then we launch this into orbit. Here's the orbit. Alright, here's the orbit. And same satellite. Now I have a force acting on it, which I'm going to call F2. Okay, so what is the ratio of these two forces? What is the ratio? F1 to F2. F1 over F2. If the altitude of 320 kilometers. Let's give it a name, altitude. Let's call it H, like height, altitude, right? 320 kilometers. Okay? It's this length here, this altitude, H. Height above the ground, right? That's H. 320 kilometers. Okay, so how do we find the ratio? Now, what do we not know? Well, we don't know the mass of the satellite, right? It's not given. Probably we don't need it. Okay? Earth, well, we can find Earth's mass in a table, which I'm going to call capital M. Do we need it? Maybe we do, maybe we don't. We're going to find out. Okay? But here's what I'm going to do. I need the formula for gravitational attraction. Let's start there. So, the gravitational force between two masses. Okay, F in general, or Fg, is equal to, well, we have, if you remember from the video last time, we have a universal constant, Newton's universal constant for gravity, and then you have one of the masses, m1, let's say, and then m2, and you divide this by the square of the distance between them. Okay, so you have m1 and then m2, and then you need the distance between m1 and m2, and you got to be careful here. Okay, the distance is measured from the center of each body. It can be the geometrical center, or in general we call it the center of gravity. It could be off-centered, but it's pretty much not the distance from the surface. Okay, that would be not r, but r is measured from here to there. Okay, so this F then, no matter how different M1 and M2 are, these forces on M1 and M2 have to be equal to each other, according to Newton's third law, action-reaction. Same force, Fg. Okay, so this is the gravitational force formula. This is the formula we need here. So let's apply the formula for F1 and F2 and take the ratio. Let's see where that takes us. Okay, so I'm just gonna come here and write F1 divided by F2. Okay, so F1 will be the force between Earth and the satellite. Now, what is R in that case? Well, I didn't draw this picture to scale, but Earth has a center, obviously. This is the radius of the Earth, RE. Okay, RE. Is RE going to be the R in this case? Now, RE is a large number, okay? More than 6,000 kilometers. The satellite is maybe the size of, a car or something, or even smaller. So that's negligible compared to the radius of the Earth. So there's no harm in taking this R, the separation between the masses, or the center of masses, as this RE here, okay? So for R1, I'm just going to write here G times mass of M1 means the Earth, capital M, and M2 means the satellite, little m, divided by RE squared. Okay? I'm done. That's F1. When it comes to F2, though, I'm going to repeat it, the same formula here. Earth's mass is still there, capital M, and little m stands for the satellite mass, no change there. But now, the distance between the satellite and the center of the Earth is RE plus the altitude, which was h, right? So RE plus h, and I need the square of that. All right? So that's what you have to be paying attention here. The distances, how we measure them, okay? So when the objects are on the floor, you don't say the distance is 0 because it's on the floor. No, you have to think about the center of mass, the geometrical center of the large body, which is Earth. So you have to think about the center of the Earth. From the center of the Earth to the center of the satellite, the object, which is negligible. I mean, I'm talking about this distance here, okay? Maybe it's just 1 meter. 1 meter corresponds versus 6,000 kilometers, right? So, that's why I picked RE. That was a good approximation. But when it comes to the orbit here, this h is, I can no longer ignore it. That's 320 kilometers, okay? That's quite an amount. I'm including it next to RE. RE plus h is the distance that goes into the formula. Okay, so let's just do it quickly. What happens here? I mean, I have a fraction, right? G's cancel. M's also cancel. So I end up with RE plus h divided by RE again squared. Right? That's what you get here. Or if you will, 1 plus h over RE squared. Okay? All I have to do now is to plug in the numbers here. That's all I have to do, and take the square, and I'm done. Now I'm going to take a break after this problem. I'm just going to stop the video. And for you, it's just going to be 1 second, but I'm just going to take a break, maybe half an hour or more, for dinner, okay? So, 1 plus h. What is h? 320 kilometers. What is RE? If I'm not mistaken, that's 6,371 kilometers. I may be wrong. I have to check this number, okay? How do I check it? I check the book. Somewhere in the book, we should have the radius of Earth. Earth is not a perfect sphere, so they either have the radius at the equator, or they have an average number, which should be fine for our purposes here. So let's check the appendix. In the appendix, we have reference information, periodic table, unit conversions, and we have universal gravitational constant. We don't need that. Well, that was appendix B. What about appendix A? Okay. Well, we can Google it. That's the most direct way, right? Okay, maybe the index here. Earth radius. Okay, so maybe some chapter here. Okay, Earth's radius is 6.37 times 10 to the 6 meters. It says 6.37. Okay, I think I was right. Okay, so 6,000. So let's write it down. 6.37 times 10 to the power 6 meters is equal to 6,370. I think 71 should be the correct kilometers. Okay, so kilometers cancel. Let's just find it quickly. I'm going to take a break after that. So 320 divided by 6,371. Add 1 to this number and take the square. This is 1.1. 1.1. Alright, so the force F1 is greater, obviously, and this is what they wanted us to find. Find the ratio of Earth's gravitational force of a satellite when it is on the ground to the gravitational force exerted when the satellite is orbiting at an altitude of 320 kilometers. The ratio is 1.1 or 1.102977, goes like that. Let's check it. It's 59, an odd numbered problem. And I'm going to take a break after that. So, chapter 2, 59, 1.1. Okay? Alright, so I'm gonna, should I upload this or should I just, I'm gonna upload it, okay? I'm gonna upload it, and so I'm gonna stop it and record maybe another video for the rest of this chapter, okay? So, till next time, goodbye.